On to another edition of the ZX Calculus seminar after a break last week for the QPL deadline. And I hope everyone managed to finish their papers on time. So today we have Tom Ewen, who will be talking about an application of ZX Calculus to quantum architecture search. So please, Tom.
Yeah, thank you for inviting me here. As I said, my name is Tom Ewen, and I'm going to present our paper about application of ZX calculus to quantum architecture search. That's now just something short about the authors. This is a joint work together with Ivica, Patrick, and Oliver. We are all four from the Fraunhofer Institute for Applied Mathematics, ITWM in Kaiserslautern. Here's the link to the paper. It has just been accepted to Quantum Machine Intelligence, so hopefully in the next days there will be a reviewed and updated version available under this link. And also for references and more technical stuff, I would refer to the paper. Today, here's a short overview of what I want to talk about. As this is the ZX Calculus seminar, I'm expecting that most of you know more than me about the ZX Calculus itself. So I will focus this talk more on our motivation, why we used it, what we want to do with it, more about quantum architecture search, and present some results. If you have questions, feel free to ask anytime. Okay, starting with the motivation, where we're coming from. So the idea, what we wanted to do, it was to learn function with parameterized quantum circuits. This has been done before in the literature for different types of problems, for regression problems, for classification problems. Here, when we talk about function learning, it's basically a regression problem. And we have one problem, complexity of the circuit we use versus the approximation quality we achieve. So basically, if we make the circuit arbitrarily complex, we can basically approximate these functions as good as we need to approximate them, at least if we ignore any sources of noise. Theoretically, we can approximate very well. But we will come to circuits that are very deep, very wide, that are very prone to noise, maybe not even executable on current hardware. So there's always this trade-off between the approximation quality we reach and the complexity of the circuit. Just here in the plot, a very short visualization, how this function learning could look like for first a very simple circuit, and then just making it slightly more complex, we directly see that the approximation of the function becomes a lot better. And the idea here that we started to investigate is quantum architecture search. We want to find now specific parameterized quantum circuits that are able to solve one specific problem in an efficient way, meaning with a not very complex circuit, have a good approximation quality for this one specific problem. And the idea is that we do this iteratively. We start with one defined circuit in the beginning, and then randomly modify that circuit, see if the approximation improved. If it does, we accept this new circuit and repeat this step until we are satisfied with approximation quality. And here's some pictures how this could look like. Again, starting with a very simple circuit. Then here, one additional step we usually did was finding out if some of the gates that we used do not really benefit the approximation quality, so we can leave them out. So you see in this one step, some gates are removed and some are added. And you directly see that the approximation quality improved. Then we make the circuit even more complex, get a better approximation, and we can continue this basically as long as we want, making the circuit more complex and getting a better approximation quality. Doing it like this, it basically goes only in one direction. We increase the complexity and also increase the approximation quality. But as I said, it's a trade-off between these two qualities, and maybe you could introduce more characteristics of the circuit that somehow characterize how well suited that one is. And our next step was going from this one-dimensional approach to a multi-criteria approach. And that's the algorithm that we present in the paper as a multi-criteria genetic quantum architecture search algorithm. And we have here multiple fitness criteria for such a circuit. So first of all, the approximation quality, the obvious one. Then we can take the circuit depth, the number of 2-qubit gates, or other properties. One could think about some more noise-related things, or the topology of the actual hardware we want to run this on. Or as we use it for function learning, we use feature encoding gates, parameterized gates to encode the input features. We could also take the number of these gates as one feature or one fitness criteria. And other things that change when moving to a multi-criteria genetic approach is we no longer have a single circuit that we modify, but we have a population of circuits. And now, since we have more than one criteria, the concept of one optimal one isn't valid anymore. So we talk about a Pareto front. So this is all the circuits that are non-dominated, meaning you cannot, or there is no other model that is better in one of the fitness criteria without being worse in one of the others.
Hey, sorry.
Yes,
Can I ask a question?
sure.
So, the previous slide, you said this is called quantum architecture search, right?
Yes.
And initially, I had a different idea what this would mean. Do you have any insights why this is called architecture search instead of maybe just like quantum circuit or quantum ansatz search?
That is a term that is basically copied from classical machine learning, where architecture search comes from neural networks, where you basically search for a network architecture. And since in some contexts, these parameterized quantum circuits are somewhat used similarly as neural networks or networks in general, we adopted that word.
All right, thanks.
Okay, where did I left off? Okay, so exactly in this multi-criteria setting, now we no longer have a single optimal circuit, but we have this Pareto front of optimal circuits. And one generation of this genetic optimization algorithm works always the same. We start with selecting the circuits we want to modify. Then we randomly modify these circuits, evaluate the fitness values again, and then basically check again if we have now dominated circuits that can leave out, and thus generate the next generation and repeat that step. Here you see how such Pareto fronts could look like. Here are just 5 iterations of such a genetic algorithm. And we have here on one dimension the circuit depth as one feature, on the other the mean squared error as approximation quality. And you basically see we start with iteration 1. Let me see if I can have laser pointer. Do you see the laser pointer? Perfect. We start here in the first generation, and then these points get modified. Some of them improve. Improving here means reducing the circuit depth or reducing the mean squared error. So over the iterations, the Pareto front always moves or should move to the lower left. And you can repeat this until you're satisfied with this Pareto front. So the result of such an algorithm is the Pareto front of optimal models. And then you can decide which properties are most important to you. You can have a look at this curve here and basically can decide which model suits you best. So the algorithm cannot give you one optimal circuit, but you have to decide which of the fitness criteria are most important to you, which trade-offs you are willing to make. Okay, this was a short motivation why we look at quantum architecture search, how our algorithm looks like. And until now, I only talked about quantum circuits. So next part is how the ZX calculus comes into that. The basic idea is, can we benefit from replacing the representation of our quantum models as classical circuit diagrams by ZX diagrams? since ZX diagrams are maybe more concise visualization or interpretation of quantum algorithms. The hope was that we reduce redundancy and are able to search this possible solution space of possible quantum models more efficiently by looking at ZX diagrams instead of circuits. This comes with some partly significant challenges. So first of all, at least we were lacking intuition how it makes sense to modify such a ZX diagram in this mutation step of our genetic algorithm. So how to randomly modify ZX diagram, especially if you look at extractable ZX diagrams, because modifying the ZX diagram into one that is no longer extractable into a quantum circuit does not really help us, because we need it to be equivalent to a quantum circuit to evaluate it at the end. That also brings additional computational effort. This whole genetic approach is on its own very computational intensive, and adding this extra step of computational effort of extracting the circuits from the ZX diagrams doesn't help. And finally, the implementation. There's a big ecosystem of quantum circuits for machine learning, for all the stuff we did before. And we had to find solutions how to do the same thing with ZX diagrams. Okay, now I talked a little bit about implementation, and I continue on this. So our goal is that we do regression with parameterized quantum circuits. As I said before, this basically means we have a function that we want to learn, just any function that lives on a bounded interval and also maps to a bounded interval. Our approach is we discretize the range of the function, for example, into 100 points, and get 100 pairs of values for x and f of x. This now will be our regression problem. So we want taking a parameterized quantum circuit that is added by some way of transforming the measurement result into a numerical value at the end again, but that's not the important part here. And we want to minimize the regression error we do. So basically we plug in these xi pairs, xi f of xi pairs here, evaluate the parameterized quantum circuit U for one set of parameters, calculate an error, and then minimizing over all possible parameters to find the parameters that solve this problem. The problem here is that taking 100 discretization points, every evaluation here of this cost function takes 100 evaluations of our parameterized quantum circuit. Then again, if we want to find the optimal parameters, we usually do some kind of gradient descent algorithm. That means we have to calculate the cost function for a lot of different sets of parameters for the numeric to work out. And the next shell around this is our genetic approach that has many models, many generations, where we have to do this parameter optimization many times. So basically, the evaluation of U needs to be very fast for this whole approach to be somewhat feasible. And not only the evaluation of U needs to be fast, but also the optimization of the parameters needs to be efficient. That led for us to two decisions. First of all, we work on simulators, because doing this on actual quantum hardware is, as of now, not feasible. And the other decision was to use automatic differentiation or automatic gradients. That's also a technique from classical machine learning, where we can very efficiently calculate gradients of this cost function to be able to use gradient descent algorithms that use the actual gradient, don't have to approximate them.
Can I ask a question about this?
Yeah,
So
sure.
just to clarify, by automatic differentiation, do you mean that for the gradients of the quantum circuits, you're not using things like parameter shift rules?
Exactly.
I see.
Yeah, this is something similar to backpropagation in neural networks. If you work with that, you can basically get the gradients for free if you implement it at the beginning correctly.
Yeah.
And there are libraries to do that for you. So it's actually quite easy to get this gradients very efficiently.
Yeah, a lot quicker than the circuit evaluations. I see. Thanks.
Yes, especially since this parameter shift rules, they scale very badly in the number of parameters.
Yeah. Cool.
Okay, and I'm going to go into more detail about the implementation. First of all, I don't know if the slides will be made available. If not, you have to type this link from the recording. We have made our code public for that. And it is a combination of PyZX. You are probably very familiar with that. SymPy for the parameterization, then PennyLane, JAX, and JAX-opt, the last two for the automatic gradients. And yeah, as you would expect, the PyZX library makes it very comfortable to represent ZX diagrams. Then SymPy allows us to basically put parameters into the faces of its ZX diagram. And since Python's overloading, so yeah, I haven't said that before, everything is implemented in Python. Since this overloading, basically you get it for free that these symbols are treated correctly by PyZX, and you can use many functions from the PyZX library for parameterized ZX diagrams. Then there is a plugin for PennyLane that extracts a circuit out of a ZX diagram, and also that we needed to make slight modifications, but it basically directly worked to extract parameterized circuits out of these ZX diagrams. And then we could use JAX and JAX-opt to take this PennyLane quantum circuit to very efficiently calculate the gradients. And also this JAX-opt library has very, very efficient gradient descent algorithms for actually solving these optimization problems. Any questions to that part? Okay, then I will continue and go to our numerical experiments and our results of these experiments. So as I said before, we thought a lot about how to modify the ZX graphs to actually do these mutations and change our model. There was, I think, a master thesis by Barnes that also did mutations of ZX diagrams in a more static sense, so not parameterized, but many of the mutations we got from this publication. So the first one is the local complementation. That one mutation has the huge benefit that it is G-flow preserving. So we know that this will not break extractability. That helps a lot because in the other mutations, we have some trial and error that where you just randomly do such a mutation, see if the diagram afterwards is still extractable, and reject it if not, and try again. This one always works. There's also the inverse version of them, basically just reversing the same operation. This one is unfortunately not G-flow preserving. Then this pivoting, which is basically a combination of 3 local complementations after each other. And here the fourth one is basically just adding randomly anywhere in the graph phase gadget. Then the next one is an edge flip, which basically just turns a Hadamard edge into a non-Hadamard edge. One detail I haven't mentioned yet, we always use these graph-like representations of ZX diagrams, meaning that all edges should be Hadamard edges. So this flipping, which sounds quite straightforward and like it doesn't change a lot, leads to a graph that actually did change a little bit. Yeah. And then finally, we have some other edge-related mutations. First, just randomly adding one or removing one. Finally, splitting, meaning we just randomly selecting one edge, putting a new vertex on this edge, and then afterwards having, instead of this one edge, two edges and one vertex. And finally, combination of adding and removing, where we just in one go move one edge to another position in the graph. Yeah, this doesn't, we had no intuition how well these mutations actually work. We had the big question, how much of an actual impact does such change in the graph really have on the mapping this graph represents? So we thought about how could we get information about how much one mutation actually changes. We first thought about, well, we could calculate the unitaries that they represent and look at some metrics between unitaries, how different they become by these mutations. But we quickly came to the first result that this will be very complicated for parameterized graphs to get the unitary itself and then getting a sense of the distance between two unitaries in a parameterized sense. And as we do that for a regression problem, the unitary itself is not really what interests us. Therefore, we did more numerical experiments. So we defined a set of benchmark problems. Just here, you see the functions we introduced. So there's a jump function, something linear, exponential, logarithmic, ReLU function, something polynomial, and a truncated Fourier sum, just to have a wide variety of different functions that could be of interest. And then we generated random ZX graphs. So again, very helpful that PyZX library offers functions to generate these. We generated them and then replaced some of the phases by parameters to get random graphs. Then for every random graph we generated and every test function we have defined here, we trained the parameters, noted down the approximation error, and then mutated this graph. And if the mutation was successful, we repeated the parameter training and again recorded the approximation error we have now. And then we compared these two approximation errors. So basically we looked for every mutation at how much closer or farther away we got from the target function we are interested in. And we looked at that for all the different test functions. Repeated that many times. And in the next step, I will present the results, what came out of these mutation experiments. So the first visualization I give you is here for every function. Ignore that the lines don't mean anything. So the points in between, there's no interpolations, just to see the order of the points. So as long as lines are not crossing, the order doesn't change. So that's what the lines are for. And it basically gives for every test function and every kind of mutation, the average absolute improvement we observed on the random graphs we generated. So what you, for example, see is that the jump function generally had a better improvement by these mutations than other functions. And you also see that, for example, the phase gadget addition had always the biggest impact, while here, for example, the edge swap had the lowest impact. What our basically takeaway was that, except maybe from here, maybe this polynomial and the difference between exponential and Fourier, that mainly there are no special combinations of mutations and functions that work especially well. So the idea here was to see, okay, does it make sense to use some mutations for specific target functions, or does it maybe not really matter how the function looks like, which mutations one should use? And we basically came to the conclusion it does not really matter. The next experience we did.
Sorry, Tom. I'm not
Yes.
sure if you can see the chat, but there was a question there.
I
The
don't
question
see
was,
the question, sorry.
yeah, the question was, what are the X-log and X-polynomial mutations? But I think it means those are the types of benchmark circuits, right?
Exactly. Here on the x-axis are the test functions. So going back here, the exponential function, this one. And the different colors are the mutations. Does this answer the question? I actually don't really know how to see the chat, so maybe you have to translate it for me.
No, that's fine. If there's another question there, I'll make sure that
okay, thank you.
Arrives at you.
Okay, here I left off. So the next graph is maybe a little bit more involved to see which information we put in there. So yeah, I try to explain as best as I can. If you have questions, feel free to ask. While doing these random graphs and mutations, we recorded some properties of the graphs. So first of all, we recorded how many qubits does this graph represent? How many edges do we have? How many vertices do we have? What is the connectivity? So how many of the possible edges are in that graph? These values we recorded, and then we wanted to look at if these properties are correlated with the performance of the different mutations. So basically say, okay, are there mutations that work better in highly connected graphs or in not very highly connected graphs? Questions like this. And these here are the results. So the first bar is always the average of the thing we looked at. So the first graph here is the success rate. So the first bar just says for that mutation, so here in the first column, the local complementation, 100% of the mutations worked. As I said before, this one, we know that theoretically always should work, and we see in the experiment it does. That also says, okay, all the other things we looked at, so the connectivity, the number of vertices, and the number of edges have no influence on the success rate. Since it's always successful, there's no correlation between them. For the next one, it looks different. So for example, the pivoting almost always works, but it works less often the more qubits the graph has, and it works more often the more vertices it has and the higher the connectivity is. And here the mutations are sorted by their success probability. And in all rows, the order is the same. And the second row gives the same analysis of correlations, but now not to the success rates, but the absolute improvement. So how much did the regression error actually change due to this mutation? And the difference between the second and the third row is that in the second row, a mutation that fails is regarded as zero improvement. And in the third one, we ignored all failed mutations. Here, for me, the important takeaway is we see that some mutations, for example, the edge swap, have in the second row almost no impact. It looks like they don't give any benefit here. But if you look in the third row, especially the inverted local complementation, you see that if it is successful, it has a very big impact. So in this specific case, if it is successful, it has the highest impact. So this led to the heuristic in our algorithm that we try the mutations just. So we used all of these mutations, even the ones that have very low success probabilities, and just repeatedly tried them in the hope that if it actually succeeded, it has a big impact. And also another argument for it being a good thing that there are some mutations that have a low impact on the change is, and it becomes very heuristic here, and we haven't proved anything, but it's just our interpretation is that in the beginning of that algorithm, when we have a very bad approximation of the function we are interested in, then maybe mutations are more helpful, that have a big impact and change a lot. And once we are very close, it maybe makes sense to have mutations that only change a little bit to get the last fine-tuning with smaller steps. But this is something for further research to maybe look into switching which mutations one uses depending on how well the algorithm already performs. Yeah, that's the conclusion. What I already said is that there's mutations that fail very often have or tend to have a bigger impact on the actual performance of the approximation. Okay, that was it to the experimentations on the isolated mutations. The last two slides are just the results of the complete process of the genetic quantum architecture search. It is all for the same problem I showed at the beginning in the plots. So just for completeness, since we are all the authors are from the Department of Financial Mathematics, the function that we are learning are payoffs of options. Doesn't really matter for the topic here, but the function I showed in the beginning is the payoff of a European call. And here is the result of that genetic algorithm for approximating that function, once for a circuit-based approach and once for a ZX diagram-based approach. And here on the line are the non-dominated models regarding, in the first row, the circuit depth and the mean squared error, the second row, the number of 2-qubit gates, and the third, the number of input encodings. We use these 4 fitness criteria for evaluating the model. That basically means our Pareto front is now 4-dimensional. Since I didn't manage to have a 4-dimensional visualization here on the slide, we look at the projections into the 2-dimensional spaces here, always between each of the features describing the circuit together with the approximation quality. And what you basically see is that the ZX diagram not really outperforms the circuit base, but is better in different regions of these Pareto fronts. So you see the best model regarding the mean squared error is better in the circuit-based model than in the ZX diagram-based. But the ZX diagrams reach almost as good mean squared error with much less complicated circuits, at least if you look at the circuit depth and at the number of input encodings. When you look at the number of 2-qubit gates, the ZX diagram-based approach is plain worse than the circuit-based, but the circuit depth is in this example actually quite impressive. And the last slide, this here is quite abstract, these Pareto fronts. I'm just going to show you how the circuits look at the end for 3 examples. Just going back, this will be the one with the lowest error. So this point here, it's always the lowest one. Then the one with the lowest depth, this is this one. And then the one with the fewest number of input encodings is this one here. The one with the fewest number of 2-qubit gates is the same as the one with the lowest circuit depth, therefore only 3 circuits are shown. And what you can see here, I mean, the exact detail of the circuits is probably not very meaningful now. Just note that the one with the best mean squared error is the most complex circuit, at least in the depth and the number of input encodings. And yeah, it has a significant lower mean squared error than the others. But if you look at the plots, all of these have mean squared errors that are actually quite good. And it's, for the eye, quite difficult to see just from the plots which of them is the best one. So if I now would decide which of these circuits I would want to use for an application, one probably would go here with the shortest circuit, just because, I mean, if you would try to run this on an actual device, on current hardware, the noise that is produced by current hardware is in a different order of magnitude than every error that we have here in the theoretical approximation. So one could even maybe go to even less complicated circuits and accepting more error here. Okay, that was my talk. I thank you for your attention. And
Right.
now I'm open for questions.
Thanks, Tom. Thanks for a nice talk. Yes, I already saw there was a question in the chat, so I'll read it for you. So how is this different from the ADAPT approach used in ADAPT VQE methodology?
So our main contribution, or what we did differently, was that so first of all, that we do regression is quite new in this setting. From what I've seen in the literature before, it's mainly used for classification, where let's look into a circuit where you only have these parameterized gates, where you train the parameters, but not the regression itself. Then this genetic approach I haven't seen before. But yeah, the term quantum architecture search is used in the literature, but the literature has not decided yet what term should be used. So this adaptive ansatz is the same, follows the same goals. So it's a very similar approach, but we extended it by this genetic approach, and then in this specific instance by using the ZX calculus.
Miriam?
Hi, thanks for the talk. So I was just wondering about the mutations that you've used. So presumably you want those to change the interpretation of your diagram.
Yes.
I guess, so I'm slightly confused then at the appearance of local complementation and pivoting in here, because like the way that I think about those, they change how the diagram looks, but they don't normally change, like what linear operator it represents.
You're right if you do the correct thing with the phases, which we did not.
Okay, right. Yeah,
so
that
we
makes sense.
only change the structure, but forget everything about or don't do anything with the phases, because as long as these are parameterized phases, we optimize them anyway later on.
Okay.
And the nice thing about this local complementation is that this G-flow property that we need for extractability does not care about the phase.
Yeah.
Yeah, but good question. Thanks.
Okay. And yeah, maybe a bit of a comment while we're at this. Yeah, so for example, about the phase gadget addition, I've just submitted a paper to QPL where I'm looking exactly at when can you insert a phase gadget and preserve the existence of G-flow. So it's not on the archive yet, but I'll talk to my co-author and hopefully we can have it up there soon. So yeah. So in a way that would be more efficient than just having to kind of check whether there's like just run the G-flow finding process again.
Definitely. Yes,
overall.
I'm going to look out for that.
Yep.
I have a question. So with the circuits at the end, you found optimal circuits for different functions. Did you look at any metrics between the circuits? Like were the best optimal circuits typically higher in entanglement? So did you take any metrics of that?
No.
I'd be really interested to see that. So to see if the circuits end up winning and being the optimal circuits have some higher degree of entanglement or some other metric.
Yeah, it's an interesting question. We haven't looked at it only at these. I mean, this number of 2 qubit gates is probably somehow related to entanglement, but yeah, should be interesting to look at that specifically.
If there's no more questions in the audience, I have a couple of questions I'd like to ask. So I'm a little bit confused about what this input encodings means. Is this sort of how you give the input to the function? How is this translated into parameters?
Yeah, so the distinction between parameterized gates and input encodings gets a little bit fuzzy in this SetX-based approach, because some of the operations just join gates together, and then we have gates that have parameters and data points in it. But the original idea from the circuit-based approach is that since we do regression, I mean, we have here, this is the result of that circuit. So we discretize here this range and have many points, and then we evaluate the circuit for one X value, and the input encodings are gates that depend on that X value. So basically, if we want to evaluate for X equals to 50, then everywhere where here is an X, we put in, we have to scale it down so it makes sense for a parameter in the gate. But basically, we put this 50 everywhere in the circuit where the X comes across. And these gates we call input encodings. Why we especially look at these input encodings has, for us, a little bit historical reasons, because the previous paper we worked on used some controlled operations to get the input encoding into a control register, and there the final circuit complexity scaled in the number of input encodings. Therefore, this is an important feature for us. Yeah, in this specific setting.
So you could imagine that you want to evaluate this rectilinear function on a superposition of input states, and then you could sort of encode the superposition as a quantum state, and then like wherever this like X0, I think you call it here, wherever this appears, you kind of make it a controlled gate based on the value of X0. Yeah.
Exactly. So this was an idea from our previous publication, where we basically, you can replace one rotation that has an X value in it by a control register, where you can actually even load a distribution for that value. So that was our idea, to get expectation values of this function, which is then option pricing. So that's where we're coming from. And replace one rotation by this X by, if we take 3 qubits for discretizing the input value, by 3 controlled operations, and you can tune it that, so if you match the discretization and the rotations that you then control, then you will have the same result, no matter if you put the X value in the control register or directly into the qubit, directly into the rotation.
So if you care about minimizing number of input encodings, because like they could correspond to controlled phase gates, wouldn't a nice metric be 2 qubit gates plus qubit encodings instead of optimizing each separately, since each of them would correspond to an entangling gate?
Yes and no. So yes, they are related, but we looked at them individually, because actually if you use that control register, the number of 2 qubit gates you get per input encoding scales in the discretization of the input register. So for us, it made sense to have it separately, because basically the input encodings are worse than the 2 qubit gates, since they scale. If you take 100 discretization qubits, you have 100 controlled operations per input encoding. Therefore, we looked at it separately, but maybe one could even argue that if this discretization becomes fine enough, the fixed 2 qubit gates stop matter entirely, because they are just dominated by the other number. But there are other possible fitness criteria one could look at.
And just to check, how do you read off the function value from a circuit? Do you measure and then you interpret the probability distribution, like the expected value, as the outcome of the?
Basically, yes. So we tried different approaches. So the easiest is just measure only 1 qubit and take the expected value of that. If we have many, we take Pauli Z observations on all of them and take the expected value of that, and then scale back to the actual range of the function we want to use or we want to approximate.
Do you observe that one of these gets more complicated circuits? I could imagine if you use more measurement outcomes, this allows you to more easily encode complex functions.
I had the impression it does not matter too much. What happens is that there are unnecessary gates happening if you only measure one qubit, because this, especially with the ZX graphs, it is not straightforward how to prevent that if you only measure the first qubit, how to prevent gates that operate on the qubits that are not measured and not entangled afterwards with the qubit you actually measure. So therefore we decided to measure all. But I mean, it would also be very easy to manually just in the end remove all the gates that cannot impact the result. Yeah, but we haven't observed a very heavy influence of the how do we measure it in the end.
I can continue asking questions, but other questions in the audience that people want to ask. Okay, then Tom, if you don't mind, I can keep going.
Yeah, I'm happy to answer more questions.
Okay. Yeah, so I wasn't entirely clear on sort of the full procedure of what the order of operations you're doing. Like did you start with a circuit and you represent it as a ZX diagram, and then you mutate the ZX diagram by applying graph operations, but you only keep the diagram if it can be extracted into a circuit again? Is that sort of what's happening?
Yes. So, yeah, maybe in a little bit more detail. So we start with just any ZX diagram that can be extracted to a circuit. On that diagram, we form the mutations. We actually did it stochastically, where we say, okay, each mutation has in every step a fixed probability to happen. Then we apply these mutations, try for every mutation, we apply it, check if it afterwards is still extractable. Then there, again, very heuristically, but I think the number is 10. We just try 10 times because the position where this mutation occurs is randomly chosen. So we try different positions, see if first time one works, we take that, then we try for the next mutation and do it like this. And after, so each mutation is applied with a certain probability. And if this is done, then we extract the circuit, evaluate the fitness criteria. Then this procedure is done if this circuit survives to the next, or this diagram survives to the next generation. And then one generation is finished and we start again mutating.
And then you evaluate by doing some symbolic stuff on this diagram. You don't actually calculate a linear map underlying it.
We actually transform it to a circuit and then evaluate that circuit.
Yeah.
And we also, I mean, all these fitness criteria, like depth and number of gates and stuff like this, I mean, it's all related to the circuit and not the ZX diagram. So we have to translate it to a circuit, calculate that stuff on that circuit, evaluate it I mean, we calculate these points. We have to do the whole parameter optimization. We actually do the parameter optimization on the circuit and not on the diagram. And then we get the fitness values for that diagram.
And so I think you mentioned at the start that your goal was that you hoped that using ZX diagrams, you could explore the space faster than with just circuit mutations.
Yes.
Do you observe this in like training time or convergence rate or anything like that?
Not really. So the benefit, so looking at this plot here, they had the same time available to get to this result. So it's not number of generations or something like this. We just said, okay, same machine, same time, which results do we get? And yeah, so I would not say that this initial hope for using the ZX calculus, we can now definitely say that it holds true. but we see this trend that we have less complex circuits with similar performance. Yeah.
I believe there was a question again in the chat. So this is a question about your paper, apparently.
Okay.
For figure 2 inside your paper, why are different functions used for evaluating the change introduced by a mutation? Do you evaluate using all functions during actual training runtime?
Okay, so we have to separate. So it's probably figure 2. Yeah, we have it in the slides here as well. Should be this one. So we have here 2 different experiments we did. So this here is where we really looked at the individual mutations, and the results I showed at the end is for one specific problem where we use this whole genetic algorithm to get the result for one target function. So in these mutation experiments, we applied the mutation to each and every test function to just see how well these mutations individually perform. It only looks at one mutation step. For this complete genetic algorithm, we always have one target function that we train the circuit for. So the result of that algorithm is really only usable for this one target function we put in at the beginning. So it's not about finding one generic ansatz that can solve many problems. So the idea is not to find one circuit that can solve all these test functions. The test functions were just for evaluating the mutations itself. The whole quantum architecture search algorithm searches for one parameterized circuit that can solve one problem very well.